Hi, I'm Ahmed Dawood, and in this session, we are going to discuss how we can train logistic regression. In the last session, we have seen what is logistic regression and how it is uh, different from the linear regression, and how the equation of logistic regression is obtained from the equation of linear regression. In the end of last session, I recommended you to have a look on the training sessions of linear regression in which we have discussed two processes. One was gradient descent and one was normal equation. Okay, and I told you that there is a difference in the processes of training processes of linear regression and logistic regression. So there is no such difference in the process of training, but there is a difference in the cost functions of linear regression and logistic regression. Okay, and I will also give you the idea about these terms, about the difference of cost function of both models, linear regression and logistic regression, and I will also give you the reason for that. Just to give you a recap of gradient descent, what was the gradient descent in the case of linear regression? When we have to train some model, we have to design some cost function. Okay, cost function, sometimes we use the name cost function or error function or loss function. These terms we simultaneously are using. Just the concept is the same, that to obtain such a best fit model, we have designed some error function equation, and we will try to minimize that error function. In the same way, we have considered in the case of linear regression error function SSE, or mean square error, yeah, which is in this way, the difference between the actual value for a single point, the difference between the actual value and the prediction value. Okay, then we have, if we will take a summation of that after taking squares, so it will become a sum of squared, and if we will take average of the squared errors, then it will become mean square error. Okay, then these functions we can consider as a cost function, and then when we are interested in the best fit parameters, okay, these equations will be like this. Yeah, like this. Okay, and we are interested in these parameters in M and C, and parameters where the SSE is minimum. Okay, and we have studied algorithm which was a gradient descent. How it works? First, we have to about the concept, and if you are again you want to revise that concept, you can go back to the session of gradient descent. But for now, just am giving you a quick recap. In the gradient descent, we just follow these four steps. First, we have to initialize our parameters. Randomly, we can initialize that parameters. Then calculate the partial derivatives of cost function with respect to each parameter. Then we update our parameter values in this way. We are updating our parameter values, having some learning rate. Then we will repeat our step 2 and 3, means we again after updating parameters, we again calculate partial derivatives, again update parameter, and these two steps, calculating the partial derivatives and updating the parameters, we repeat this process until we get our parameters for the best fit model. Okay, this was actually the process of gradient descent. And the curve or the function is the mean square function or sum of square function is looks like that, the ball shaped functions. Okay, ball shaped function in which we know that it has it is a convex function, and it must have some minimum point. Like here in that case, the minimum the error has minimum value at this position, where I have drawn that line. By considering the nature of that function, we proposed another solution, and the persons of machine learning has proposed another solution, which is the solution of closed form solution. As a closed form solution, the person of ML have proposed by considering that equation. Okay, they got an idea that this function must have some minimum point, and it will have minimum point where the slope is zero. Where the slope is zero, at this position their SSE will be minimum. Then if we will make take partial derivatives of our SSE and make it equal to zero, then we can get our M and C where SS is E is minimum. That's why we also call it as a closed form solution, direct solution, and the equations that we obtained we usually call as a normal equations. Okay, so we got number of equations according to our number of parameters, and then we will solve that equations, and we got parameter values directly without iterating the process. Okay, we just make partial derivatives equal to zero. So these two processes we have discussed in the training sessions of linear regression. Okay, now we will have a look on the training of logistic regression. Okay, so in the case of linear regression, we have some cost function, which looks like that. Uh, the difference between actual values and the difference between the prediction. Okay, and sum of all the differences, or you can say sum of all the squared differences will become our cost function. Okay, and SSE will become, and if we will take average, it will become MSE, and you can use it's up to you whichever cost function. Okay, then you will minimize that cost function for the sake of getting the parameter values where the this SSE is minimum. Okay, so this was the case of linear regression. Now we will try to analyze in the case of logistic regression how if we will try to, or you can say in the case of logistic regression, how our cost function will look like. Okay, how what type of cost function will be in the case of logistic regression. First, we will try to build a cost function in the same way that we have done in the case of linear regression. Okay, and you will see here. In the case of linear regression, we have cost function in that way, summation of the square differences between actual values and the prediction values. Okay, and we call as errors. Okay, and some summation of all errors. Like here, in the case of the logistic regressor, the error will be like that. Error for a single instance. Okay, for single instance, the error will be like this is the actual value. Let's say we are considering just point number 0. So error 0 will be actual value y0 minus our prediction value. Prediction value will be in this way, 1 over 1 plus e raised to power minus, here will be m x 0 plus c. Okay. Just because we are considering the 0th point. Okay, so for the single instance our error will be like that. Okay, just because that we have our models equation here in this way instead of simple linear equation. Instead of that equation we have this equation here. Now our error will be like this for single point, and if we will sum all the points in the form of squared, then it will be like this. Just make a square. Okay, so our cost function, this is our cost function, and we have designed this cost function in the same way as we have done for the linear regression. Now we will have a look what actually this cost function has a difference, and what are the disadvantages of using that cost function. Okay, so first of all, this function is not always convex. Okay, here the equation is now the equation of SSE become different because here e raised to power some terms are involved. Okay, here e is involved, some logistic function are involved in the SSE. So this function, particularly this function, is not always convex. What is actually means by that? It means that we cannot get a single solution for that. Okay, when we will run the algorithm like to minimize that cost function, we cannot get the parameter values you can say parameter values where our SSE is minimum. Okay, it can give multiple parameter values, and you can say it will the equation will be your graph will be like that, and you may fall in some sort of local minima instead of some global minima. Okay, let's say it's not exactly the same as the graph will be, but just to give you an idea, if let's say your graph will be like this. Okay, now this is also minimum point and this is also minimum point. Okay, but this minimum point, this is lesser than that value. Okay, this is you can say this is a global minima. Okay, this minimum value is minimum of all the minimum values of that graph. Okay, and this is local minima. So this function will have graph like that, and we can get parameter values where our model is not best fit. Okay, so and there is also difficulty uh, you can say difficulty in finding global minima if we will consider this as a cost function. Okay, so if we cannot consider that cost function, so what now we should do? Okay, so okay, there is another solution which is cross entropy or log loss function. Okay, this function we can use as a cost function of logistic regression. Okay, just like in the linear regressor we have error like this for single instance y0 minus our let's say mx 0 plus c. Okay, our error is like that for single instance. In the same way, the error for the single instance is in if we will consider cross entropy or log loss function as a cost function of a logistic regressor, then the error for single instance will be this one. Okay, just consider in the way, if your actual value, okay, this first I will explain you what it actually, this is a cost, this is a cost for just a single instance. If your true value is 1, then the cost function will be this. If your true value is y is equal to 0, then your cost function will be this. Okay, I will explain to you in a while. First, you can consider in the case of linear regressor, if your prediction is far away from your actual value, then your error will be high. Okay, your error will be high in that case. In the same way, if your actual value, here your actual value is 1, but your prediction, your probability is closer to 0, okay, or you can say away from 1, then this probability is closer to 0, and the log of 0 will be, if you will see this is actually the graph of log function. Okay, when you will take a log of 0, log of 0 is very high. Okay, if uh, you will see that log graph, it never touches the y-axis, but it become closer to y-axis. When your actual value is one, and but your prediction is closer to zero, then your log of zero will be very high. Log of zero will be very high, and in this way you can say is your cost will be very high when you have actual value 1 and prediction value close to 0. In other words, in the other way, when you have your actual value as 0 and prediction your prediction, let's say closer to 1, then then your cost will be here minus log 1 minus, it is closer to 1, 1 minus 1 minus log of 0, and again your cost will be very high. Okay, now if your actual value and your probability is closer to each other, let's say your actual value is 1 and your probability is 1, then your cost function will be minus log of 1, it will be closer to 0. That means that your cost is closer to 0, your here error is very low. Here from the graph you can see the log of 1 is closer to 0. Here you can see this is 1 and log of 1 is 0. Okay, so that's why you can consider that error function. This is the error function for a single instance. Okay, if you want to consider for all the instances, then you can use that error function in which you have a y log p, which is probability. This y will be a true value, and this will be 1 minus y log into 1 minus p cap. Okay, so this will be a cost function of your logistic regressor. When there is your actual value is 1 and your prediction value will be 0, then this cost will be high. And when your actual value is 0 and your prediction is 1, again your cost will be high. When your actual and prediction values are similar to each other or closer to each other, then your cost will be low. In the same way, you can consider it as like a error. Okay, if your actual value is this one, if your actual value will be closer to this, your error will be low. And if your actual value will be far away from your prediction, then your error will be high. Okay, in this way you can consider that cost function. Okay, so sometimes you will see in some books and sites this error function uh, called as a cross entropy or log loss function. Okay, people are using these names simultaneously for that function. Okay, or in simple terms you can say for the cost function of logistic regression is cross entropy, or you can say log loss. Okay, now here one bad news for you and one will be good news for you. Bad news is that, like in the case of linear regression, you can also calculate the best fit parameters by closed form solution, by direct solution, or by normal equation. But here you cannot uh, calculate some solution or best fit parameters directly. by using some normal equation or some other type of equation, because there is no noun closed form equation here. Okay, now you cannot calculate directly your best fit parameters for logistic regressor. Okay, but the good news is that you can for the cost function log loss is the good news is that this function is convex, and this function is convex, then it is guaranteed that it should have a minimum point, it should have a global minima, and you can find that global minima by running the algorithm which we already have studied in the case of linear regression, the algorithm gradient descent. And you know about the gradient descent, you how you can use that. First you have to initialize your parameters randomly, you can initialize, then you have to take a partial derivatives of your cost function with respect to each parameter, then update parameter, again take a partial derivative, again update parameter, again take a partial derivative, again update your parameters, and this in this way you will iterate that process until you will get your best fit parameters where your cost function will give you minimum value. Okay, for example here this is I have expressed that cost function or written that cost function in the form of theta. Okay, you can also express your you can also write your logistic equation of logistic regressor in that way. P cap is equal to 1 over 1 plus e raised to power minus here will be the equation like that y cap j into 0 up to n theta jxj. If you have multiple features, in that case your equation of logistic regressor will be that. Okay, and when you will instead of p cap you will write your cost function uh, by the putting the values of that cost this here, you can write this cost function in this way. And if you will take a partial derivative with respect to some parameter theta, your equation will be like this. No need to go to remember these equations. Okay, just you can remember that cost function if you want. Okay, this cost function just you need to remember, but there is no need to remember all the how what is the equation of partial derivative, because it is just to give you the concept, the idea how the process is carried out. uh, but in the case of when we have to do some practice, or in the case of practical, we just have to import libraries from some sites or some modules. We have to use a built-in models. We don't need have to code for each model manually, you can say. Okay, so for now, in the next session we will consider very simple example how we can use logistic regression when we are doing some coding, and we will also see a documentation of logistic regression provided by the sklearn. Okay, just a quick recap of that session. Maybe it will become a little bit confusing for you in that case of cost function. You can consider that cost function. You can stop the video at the cost function, and you can also have a look of on that. But here I can repeat for you. The cost function for a single instance will be like this. If your actual value will be 1, your cost function will be minus log of p cap. Yeah. And if your actual value is 0, then your cost function will be 1 minus p cap. This is just for this single instance. For the whole number of data points, then it will be become like this. Sigma I from 1 to m, and it will become y I cap log p cap plus 1 minus y cap log 1 minus p cap, and that's it. Okay, your cost function will be this. You can consider that cost function for all the data points or data instances, and you can when you will put the values here, you can also get the idea how these are achieved. Okay, like here, if your actual value is, let's say your actual value is 0, you will put here 0. Your actual value is you can build four cases here. If your actual value is 0 but your predicted value is closer to 0, or predicted value is closer to 1. Two cases here. In the same way, two cases when your actual value is 1 but your prediction is closer to 0, or your prediction is closer to 1. You can have four cases. Okay, in that case, where your actual and prediction are closer to each other, your error will be minimum. Okay, your error, you can say in that way, your j will be minimum in that case. And also here, your j will be minimum. And when you have this here, when your actual and predictions have a difference, then your j will be maximum. And here also your j will be maximum. You can put these values and you can analyze easily. Let's say in the case of y is equal to 0 and probability closer to 1, you will see here y is equal to 0, this term becomes 0. Now you will have just this as a cost function, and you can also see in the case of y is equal to 0, your cost function is this. Okay, and 1 minus y uh, cap and y cap is equal to 0, so it will become just this one. Your cost function will become this one. Now here log into 1 minus 0, and it will be a log of 0 or log of 1, sorry, log 1 minus 1 minus 1. Yeah, in that case it will be log of 0, which will be, here you can see it will be very high. Okay, okay, I hope you got an idea about that. You can also see other three cases, and you will get your this equation can easily convert into that way if you will consider 1 point. Okay, this equation is when you are consider all the number of points, all data points. Okay, by the way, this is not necessary to have to remember everything. Just to you have to understand the concept why we are using here different cost function in the case of logistic regression. The reason I told you that the if we will use the cost function like mean square error, sum of squared error for logistic regressor, the this cost the cost function MSC or SSC in the case of logistic regressor is not convex, so we have to use another type of cost function. And we have seen we have used here the cross entropy loss as a cost function. When you will use cross entropy as a cost function, you can get you cannot get a closed form solution, but you can get a solution by using gradient descent. Okay, and how what is the concept of cross entropy? You have seen that if your it is giving you the same idea as the error will give, or error is usually give. If you are away from your actual value is away from your prediction, or your prediction is away from your actual value, then the cost will be high. uh, and if your prediction will be closer to actual value, then your cost will be low. Okay, in the next session we will do some coding, how we can import logistic regressor from sklearn, what are the parameters in the documentation of logistic regression by the sklearn, and we will have a look on that. So for now, thank you.